In recent years, a series of high-profile engine failures has rocked the automotive industry, affecting millions of vehicles from some of the world's largest manufacturers, including General Motors, Toyota, Honda, and Hyundai, along with its affiliate Kia. These issues have prompted extensive recalls, federal investigations, class action lawsuits, and widespread consumer concerns about vehicle safety and reliability. The problems often involve premature wear of critical internal components, such as bearings and piston rings, leading to symptoms like unusual engine noises, loss of power, stalling, seizures, and in severe cases, fires or catastrophic breakdowns. While each company's situation stems from specific manufacturing defects, a common thread appears to be the challenges of producing modern, high-efficiency engines under tight tolerances and regulatory pressures for better fuel economy and lower emissions. As of early 2026, regulators like the National Highway Traffic Safety Administration continue to probe these failures, with some investigations expanding beyond initial recall scopes to potentially include even more vehicles. Owners have reported incidents occurring at mileages as low as a few thousand, eroding trust in brands long associated with durability and prompting questions about long-term design and production practices. General Motors has been at the center of one of the most scrutinized engine crises, primarily involving its 6.2-liter V8 L87 gasoline engine, which powers a range of popular full-size trucks and sport utility vehicles. This engine, produced at the company's Tonawanda propulsion plant, has been linked to widespread reports of connecting rod and main bearing failures, often resulting from manufacturing defects in the crankshaft and connecting rods. Initially, in April 2025, General Motors issued a voluntary recall identified as 25V274, covering approximately 721,000 vehicles worldwide, including models from the 2021 to 2024 model years such as the Chevrolet Silverado, 1500 Chevrolet Tahoe, Chevrolet Suburban, GMC Sierra 1500, GMC Yukon, extra-large Cadillac Escalade, and Cadillac Escalade Extra Sport vehicle. In the United States alone, this affected nearly 600,000 units, with the company acknowledging supplier-related issues that led to sediment contamination and out-of-specification dimensions on crankshaft journals, causing premature wear and potential engine seizure. By late 2025, the National Highway Traffic Safety Administration's Office of Defects Investigation had received over 1,157 complaints of bearing failures, including instances of complete engine loss at highway speeds, which heightened crash risks. This prompted an engineering analysis in October 2025, expanding the probe to an additional 286,000 vehicles not covered by the initial recalls such as 2019 and 2020 models, potentially pushing the total impacted fleet toward 1 million or more. General Motors reported identifying over 28,000 field complaints in the United States between April 2021 and February 2025. With 14,332 involving loss of propulsion and 12 crashes or injuries potentially tied to sudden failures. Some owners described engines failing with as little as 1,000 miles on the odometer, accompanied by knocking sounds, oil pressure loss, or total seizure, sometimes stranding drivers in hazardous situations. In response, the company has implemented remedies including switching to a thicker 0W40 engine oil to mitigate wear. Though critics argue this is merely a temporary band-aid rather than addressing root causes like inadequate cleaning of machining debris or quality control lapses. Compounding the issue, multiple class action lawsuits filed between February and November 2025 have been consolidated into a single case in Michigan, with plaintiffs alleging that General Motors knew about the defects for years but failed to adequately warn consumers or provide sufficient repairs. One teardown analysis of a failed engine revealed thrust bearing problems and extreme wear, underscoring the severity. As investigations continue into 2026, experts warn that without comprehensive fixes, such as full engine replacements in affected units, the problem could persist, especially in high-stress applications like towing or off-road use common to these vehicles. Toyota, renowned for its engineering prowess and reliability, has nevertheless grappled with significant engine troubles in its 3.4-liter twin-turbocharged V35 AFTS V6 engine, deployed across premium trucks and sport utility vehicles. This power plant, designed to replace the venerable 5.7-liter V8 for improved efficiency and performance, has been plagued by machining debris left during production, leading to main bearing contamination and failures. The saga began with an initial recall in May 2024 covering about 102,000 vehicles primarily, 2022 to 2023, Toyota Tundra pickups and Lexus LX600 sport utility vehicles were tiny metal particles. or swarf from manufacturing processes obstructed oil passages, causing knocking, rough running, no start conditions, or loss of motive power at speed. By November 2025, Toyota expanded the recall under Campaign 25 V767 to include an additional 126,691 units encompassing 2022 to 2024 Toyota Tundra, 2022 to 2024 Lexus LX, and 2024 Lexus GX models, bringing the total to over 228,000 vehicles in North America alone. The issue affects engines produced at Toyota's Alabama and Tahara plants, where debris of a specific size and quantity was not adequately cleared, adhering to crankshaft main bearings under high loads and leading to wear or seizure. Independent teardowns of failed engines, including one with just 38,000 miles, revealed metallic flakes in oil pans, idler gears packed with debris, and spun main bearings, friction welded to components, suggesting potential design vulnerabilities beyond mere manufacturing oversights, such as tighter tolerances amplifying the impact of contaminants or inadequate bearing robustness. Toyota has reported recovering and analyzing dozens of failed engines, confirming that post-recall production periods still exhibited higher debris levels until improvements like enhanced cleaning processes and modified main bearings were implemented after April 2024. Owners have voiced frustrations over delayed remedies, with some 2025 models requiring full engine replacements. Over 100,000 such swaps have been documented in reports, while hybrid variants like the iForce Max remain excluded from the recall despite sharing similar architecture, prompting complaints to the National Highway Traffic Safety Administration. The expanded scope now includes vehicles built as late as April 2024, and while Toyota maintains the problem is isolated to specific production windows, critics argue it reflects broader challenges in transitioning to turbocharged, downsized engines under stringent corporate average fuel economy standards. As of early 2026, notifications for the latest recall phase were sent in January, but ongoing investigations could uncover more affected units, particularly if field data shows failures in supposedly improved engines, further straining dealer resources and consumer confidence. Honda's reputation for dependable powertrains has been tested by persistent issues with its 3.5-liter J-Series V6 engine, particularly the J35Y6 variant, found in a variety of family-oriented vehicles. The trouble traces back to a manufacturing defect in the crankshaft, where improper grinding of crankpins resulted in out-of-specification convex shapes, causing accelerated wear on connecting rod bearings and potential engine seizure. In November 2023, Honda initiated Recall 23 V751, affecting 248,999 vehicles in the United States, including 2015 to 2020 Acura MDX, 2018 to 2020 Acura TLX, 2016 to 2020 Honda Pilot, 2017 to 2019 Honda Ridgeline, 2018 to 2020 Honda Odyssey, and 2019 to 2020 Honda Passport models. This action followed 1,450 warranty claims and reports of symptoms like abnormal engine noise, stalling, reduced power, and illuminated check engine lights, with risks of crashes, fires, or injuries from sudden propulsion loss. By November 2024, the National Highway Traffic Safety Administration opened a recall query after receiving 173 additional complaints of similar failures in vehicles outside the original scope, escalating to a preliminary evaluation in August 2025 that now encompasses approximately 1.4 million units from 2016 to 2020 model years. This broader probe includes 4 reported crashes or fires and 2,598 manufacturer incidents, focusing on whether the defect extends beyond the initially identified production periods due to ongoing quality lapses at Honda's engine plants. Owners have described engines failing abruptly, sometimes with catastrophic damage like connecting rods punching through blocks, often at mileages under 100,000. Honda's remedy involves inspecting and replacing affected engines with properly machined crankshafts, but the expanded investigation suggests the problem may be more systemic, potentially linked to direct injection systems or variable cylinder management features that increase stress on components. Class action discussions have emerged with resale values plummeting for V6-equipped models from the affected eras, and experts noting that while Honda has addressed some oil dilution and camshaft issues in prior recalls, bearing failures represent an unprecedented scale for the brand. As 2026 unfolds, the National Highway Traffic Safety Administration's findings could lead to further recalls, emphasizing the need for enhanced crankshaft production controls to prevent recurrence in future iterations of this widely used engine family. Hyundai and its sister company Kia have endured one of the longest-running and most extensive engine sagas in recent automotive history, with over 3.3 million vehicles recalled across multiple campaigns for defects involving piston rings, metal debris, and related failures that can lead to engine fire seizures or breakdowns. The issues predominantly affect the new, Theta, and Gamma engine families, often stemming from improper heat treatment of piston rings or inadequate cleaning of manufacturing debris, which causes excessive oil consumption, cylinder wall scoring, and contamination of exhaust systems. A notable recent development came in February 2025 when Kia recalled 137,256 vehicles equipped with the 2.0-liter new multi-point injection engine, including 53,635 2021 to 2023 Kia Seltos sport utility vehicles and 83,621 2021 to 2023 Kia Soul hatchbacks. The defect involves incorrectly manufactured piston oil control rings that fail to properly seal, allowing oil to enter the combustion chamber and potentially contact hot exhaust components, increasing fire risks. Kia documented 409 incidents, 400 stall reports, and 4 fires by the recall announcement, with symptoms including unusual noises, knocking, power loss, or smoke. The remedy includes engine inspections, installation of piston ring noise-sensing software, and full engine replacements if damage is detected, but by August 2025. The National Highway Traffic Safety Administration launched an audit after 47 complaints alleged the fix was ineffective or unavailable, with some owners reporting continued oil burning or failures post-repair. This builds on prior recalls, such as Hyundai's 2024 campaign for 390,000 vehicles with similar piston ring chipping issues leading to cylinder scuffing and fires. Collectively, Hyundai and Kia have faced class action lawsuits alleging knowledge of these defects for over a decade, with settlements providing extended warranties but not always preventing recurrences. Owners have shared stories of engines failing at low mileages, sometimes after multiple repairs, and federal probes have highlighted 4 crashes and 12 injuries tied to these problems. As investigations persist into 2026, experts point to the company's rapid expansion and cost-cutting in engine production as contributing factors, urging more robust quality assurance to restore consumer trust in their lineup of affordable, feature-rich vehicles. Experts, automotive engineers, and independent analysts increasingly agree that the recent surge in catastrophic engine failures across General Motors, Toyota, Honda, and Hyundai along with Kia is not merely a series of isolated manufacturing mishaps, but rather the culmination of broader systemic pressures in modern engine design and production. For decades, automakers have faced mounting regulatory demands to improve fuel economy and reduce emissions, primarily through the corporate average fuel economy standards enforced by the federal government. These standards have pushed manufacturers to downsize engines, replacing larger naturally aspirated units with smaller, more efficient ones, while incorporating technologies like turbocharging and direct fuel injection to maintain or even increase power output. While these innovations deliver impressive efficiency gains on paper, they introduce significantly higher mechanical stresses, elevated operating temperatures, and reduced margins for error in lubrication and component durability. Bearings, in particular, bear the brunt of these changes, as tighter internal clearances leave less room for oil film to separate metal surfaces, making even minor contaminants or wear catastrophic. Industry observers note that the drive to meet or exceed these efficiency targets has sometimes outpaced thorough long-term durability validation, leading to engines that perform well in controlled tests, but falter under real-world conditions like heavy towing, frequent stop-and-go driving, or extended high-load operation. A primary aggravating factor across these failures is the widespread adoption of ultra-thin engine oils, often 0W20 or even thinner viscosities, mandated or strongly encouraged to minimize internal friction and comply with stringent corporate average fuel economy requirements. Thinner oils flow more easily at cold startup and reduce parasitic drag, contributing to better fuel economy ratings, but they form a less robust protective film between high-pressure contact points such as main bearings, connecting rod bearings, and crankshaft journals. In high-stress environments exacerbated by turbocharging's boost pressures or direct injection's intense combustion forces, this thinner lubricant film can break down more readily, allowing metal-to-metal contact that accelerates wear, scoring, or outright seizure. For instance, in General Motors' 6.2-liter V8 engines, reports of premature bearing failures have prompted discussions about how these low-viscosity oils may not adequately cushion components when combined with manufacturing imperfections like sediment in oil galleries or out-of-specification crankshaft surfaces. Some manufacturers have quietly shifted to slightly thicker oils such as 0W40 in certain recall remedies as a mitigation measure. But critics argued this represents a reactive patch rather than addressing the fundamental trade-off between efficiency gains and long-term protection. Automotive publications and teardown analyses from independent mechanics frequently highlight how these oil specification changes, while beneficial for emissions testing cycles, leave engines more vulnerable to contamination or inconsistent lubrication under varied driving demands. Compounding the vulnerability of thinner oils is the persistent issue of machining debris, commonly referred to as swarf, remaining in engines after production. During the manufacturing process, metal is cut, ground, and bored to create precise components like crankshafts, blocks, and connecting rods, generating tiny metallic particles that must be thoroughly flushed and cleaned before assembly. In high-volume production environments, especially when ramping up new engine families under tight deadlines, incomplete cleaning can leave residual debris trapped in oil passages, galleries, or adhering to bearing surfaces. Once the engine runs, this swarf circulates with the oil, acting like an abrasive that grinds away at soft-bearing materials, leading to rapid wear, spun bearings, or complete failure. Toyota's 3.4-liter twin-turbo V35A engine has become a textbook case, with multiple recall expansions attributing failures to excessive machining debris of specific sizes that were not adequately removed during production at plants in Alabama and Japan. Teardowns of affected engines, including those with relatively low mileage, have revealed metal flakes embedded in main bearings, oil pans clogged with particles, and idler gears packed with contaminants, sometimes causing friction-welded damage that experts say goes beyond simple oversights and may interact with the engine's inherently tight tolerances. Similarly, Hyundai and Kia's long-running engine issues spanning millions of units often trace back to metal debris from improper heat treatment of piston rings or inadequate flushing of crankshaft passages, allowing contaminants to score cylinder walls, increase oil consumption, and ignite fires when oil reaches hot exhaust parts. Modern engine architectures further amplify these risks through technologies designed for efficiency but which introduce additional stress points. Turbocharging forces more air and fuel into smaller displacements, dramatically raising cylinder pressures, heat, and load on bearings and rods, conditions that demand flawless lubrication at all times. Direct fuel injection, by spraying fuel straight into the combustion chamber rather than intake ports, improves combustion control, but can lead to fuel dilution of the oil film on cylinder walls, reducing viscosity and protective qualities over time. Start-stop systems, now ubiquitous to cut idling emissions, cycle the engine frequently, stressing oil pumps and bearings during repeated dry starts when oil has not fully circulated. Variable oil pumps, intended to optimize pressure and flow for efficiency, may not always deliver consistent lubrication under transient conditions like sudden acceleration or high loads. Honda's 3.5-liter J-Series V6, while not turbocharged in most applications, has faced scrutiny for connecting rod-bearing failures potentially linked to crankshaft geometry issues combined with these cumulative stresses, even after initial recalls addressed specific machining defects. Across brands, these layered technologies shrink the safety margins that older, larger displacement engines enjoyed, where looser tolerances and thicker oils provided a buffer against imperfections. Ultimately, many industry analysts contend that these engine disasters reflect an industry-wide push to squeeze maximum efficiency from internal combustion designs before fully transitioning to electrification, sometimes at the expense of proven durability practices. Rapid model introductions, global supply chain complexities, and cost pressures in competitive segments can lead to quality control shortcuts or insufficient real-world testing of edge cases. While recalls provide remedies such as engine replacements, enhanced cleaning protocols, or software updates to detect anomalies, they often treat symptoms rather than overhaul the core design philosophy. Switching back to marginally thicker oils or improving debris removal processes offers short-term relief, but experts warn that without re-evaluating the balance between regulatory-driven efficiency targets and robust, forgiving engineering, similar widespread failures could recur in future engine generations. As consumers grapple with unexpected breakdowns, lengthy repair waits, diminished resale values, and safety concerns, the automotive sector faces growing calls for greater transparency in how efficiency mandates influence long-term reliability decisions.